So, so let's recall what we have done so far. So let's take this problem. So given this Markov chain, so you have this probability distribution, right? So let's say we have states. So let's say we have states 1, 2, so 3 and 4. Right? Suppose we have 4 states. Right? And for between these 4 states, we are looking for a transition matrix, and this is a transition matrix that is given to you. So the question is, can we find the stationary distribution this? So can we compute this? So the question is, given this matrix, can we compute the stationary distribution? So this is to get your hands dirtier, okay? So to just give you Atul, to help you out, the stationary distribution pi is pi 1. So let's say here. So this is 4 states, right? So we have this, that pi will be equal to pi times so any vector pi that satisfies this equation is called a stationary distribution. Can you work this out then? So it's a one like 1 cross n vector that you're multiplying with a matrix which is 4 cross 1, 4 cross 4.
And that will give the vector back.
Yeah, that will give you the vector back. Can you work this out? Yeah. Yeah, so here the order is like, this 1 cross 4 vector.
Okay.
So 1 cross 4, we want a 1 cross 4 vector. So you have to left multiply, right? 1 cross 4 times 4 cross 4. So since we learned a lot of theories, so today we thought like we should work out examples and see what we have learned so far. No. How do you come up with it? So it's not a distribution, right? No, so this is not your initial distribution. So it should be a probability distribution, right? Like 1 plus 2 plus 3 plus 4 is not 1.
It's like 1 by 4, 1 by 4, 1 by 4.
No, so it could be any. So you want to figure out what if 1 by 4, 1 by 4, 1 by 4 is a stationary distribution, or it's something else. So you have pi 1 to pi 4 are unknowns, right?
Like
So those are your unknowns.
if they are probabilities now.
They are probabilities, right? So you have this additional condition that pi 1 plus pi 2 there's an additional condition that you have. So in the meanwhile, in case you're getting stuck with this, I'll give you a smaller problem. So I have another matrix P prime that is 1 minus P, P, 1 so I'll say Q and 1 minus Q. So find the stationary distribution for this. So this is a smaller question, let's say. So let's look at the second example first, and then like we'll go to the first one. Oops. So what does it mean? So I have, say, u comma v. uv is my stationary distribution. Then I have 1 minus p times. I want this to be the same as uv. Right? So what is this? Right? So what is this? So if I simplify this, I'm going to get VQ is the same as PU. So the other equation that I'll get here is I have PU plus V times 1 minus Q is equal to V. Again, I get the same equation. Right? On the other hand, I also know this fact that U plus V is equal to 1. Then my V is going to be right. So what does this imply? This implies V is right. Then what will this give you? U is nothing but Q by P plus Q. Make sense? Ajitanshu, you? All good? Good. So now we use this. Right? So this is just a system of equations that we are trying to solve. So we had 2 unknowns and 3 equations, but like this, the second equation was redundant. Similarly, we'll look at this case. Right? So let's look at this case. So what will this be? So can we go through the equations? Suppose I have, let's say my unknowns are pi 1, pi 2, pi 3 and pi 4. Right? So let's remove the commas so that I can make it a vector. Right? So what will this be? So I have pi 2 by 10 plus pi 3 by 10, 9 pi 4 by 10 is equal to pi 1. Right? And then what is the second statement I have? 3 by 10 times pi 1 plus pi 2 by 10 plus right? And the third equation is pi 1 over 10 plus
7 by 10 times pi 2 pi 3 over 10
is equal to right? And the fourth one is 6 by 10 times pi 1 plus
pi 2 over 10
pi 2 over 10
plus pi 3 over 10
plus pi 3 over 10 is equal to pi 4. Right? So you have these equations. Can we simplify? So the other way to write these things is I have minus pi 1 plus pi 2 by 10 plus pi 3 by 10 right? Similarly, I have 3 pi 1 by 10 plus, sorry, it will be a minus 9 pi 2 by 10 right? Then I have 6 pi 1 by 10 plus pi 2 by 10 plus pi 3 by 10 minus pi 4 is 0. Then pi 1 by 10 plus 7 pi 2 by 10 minus 9 pi 3 10 right? So now I have 4 equations. So I also have this pi 1 plus pi 2 plus pi 3 plus pi 4 is, so I have this 1, right? Now all it needs me to do is simplify these equations, right? You can solve it. So I'll leave the, it's not very difficult, right? I mean, so you add these two, you get pi 4 in terms of pi 1, pi 2, pi 3. And you have pi 3 in terms of pi 1 and pi 2, right? The equations are simplifying very fast. Or you have pi 1 in terms of pi 2, pi 3, pi 4. However you want to reduce it, you can reduce it. So from this equation, you can express, so rather from these two, if you sum them up and add it with this, so you get plus pi 4 here and you have a minus pi 4 here. So if you add these three, you get an equation in terms of pi 1, pi 2, pi 3. And again, so you can replace pi 4 with this in this equation. And then you get an equation in pi 1, pi 2, pi 3. And then you simplify this. So there are ways to simplify this, but, right? So this is all that is going on. So all this says is pi is a stationary distribution. If applying this same distribution with p again, will not change it. Right? So this distribution pi is invariant under action with this matrix P. So there are like, so this matrix I've actually picked it from Midzen-Markov file. So this is example, this is exercise, this is exercise 7.1. Right? And this particular problem that I'm looking at is exercise 7.2. Part of exercise 7.2. Good? So you understand what is going on? Rather, this is so exercise. Page 171 of Midzen-Markov file. Sorry?
Like we add the 3, so they are related to the fourth equation. We are getting P1 equals pi 1 equals 0, I believe.
Okay. So
So the question is not on like Markov chain. Like doubt was like why pi 1 is 0.
it could be.
It could be. It's not.
So it need not be uniform,
Yeah.
right? Satisfied with this? So let's look at this interesting problem. So let's slightly make things slightly more serious. So this is something we'll look at. The problem is the following. So we'll look at something called a simple queue. So this is modeling some examples in terms of Markov chains, right? So the first example is, so a queue is a line like that so the queue is something like you go to a ticket counter, you have a queue if you're boarding a bus. I mean, like ideally there should be a queue for boarding a bus, but unfortunately we don't, but right? So the simple queue has its following properties. So at each time step, exactly one of the following occurs. Right, the first one is So do you see this? So there's some queue that is happening. So you have a queue, and like it has this following criteria. If there are less than fewer n customers, then a new customer joins the queue, right? And if the queue is not empty, then with a probability mu, the head of the line is served, and they leave the queue. With the remaining probability, the queue is unchanged, right? So this is a very generic issue, right? Can we model this as a Markov chain? So what could be a random variable? So what could be a time varying random variable here? So think about this. So the first question is, so to define a Markov chain, so define a time varying random variable. Or look for it, right? And then what values does it take? right? And then construct the Markov chain. These are the 3 steps.
Number of customers at a point at a time t will be the random
So try to build it, so so we can discuss, so that others can also think, right? So can we? So basically, so in a graph, so Markov chain is a graph where there's a probability associated going from one node to the other.
Okay. So you're supposed to model the graph.
Yes. So it's like you model it as a probabilistic graph.
Okay. So the nodes will be the points at which the probability differs.
No, so for every node, if there are k outgoing edges, there's a probability on each of them such that the cumulative probability is 1. So we have a real world example. So can we model this as a Markov chain? So modeling your problems as Markov chain is also very important. I mean, the Q does not change. As in number of people, so basically in this case, one customer leaves. Sorry, one customer joins. Here one customer leaves. Here like there is no leaving or joining. So do you want, so what is the state space? So what is the time depending random variable that you want to define? So what is time varying is the number of customers in the queue. Right? And what values does it take? 0 to n. Right? So essentially I have an I, then I have this I plus 1 until n, let's say. So it says as long as I is strictly less than n, I have a probability of adding a customer with probability. I mean, like lambda is a probability of adding a customer, right? So this is all forward. So that is probability of pi comma I plus 1 is lambda, right? And then probability of I, so this is for all I less than n. And probability of I going from I to I minus 1 is mu for all I greater than 0. Right? So the probability of going back is mu. With the remaining probability, nothing changes. So that means 1 minus lambda, nothing changes here. Right? So this is going to be what? So 1 minus lambda minus mu. Similarly here, 1 minus lambda minus mu. What about this one? 1 minus mu. Good? Similarly, you have the same value here. So this is your Markov chain, right? So now, what will be the stationary distribution for this? So I want to compute a stationary distribution for this Markov chain. right? So this is your Markov chain. So the stationary distribution for this is, so you want, how many states are here? N plus 1, right? So I have a vector from pi 0 until pi n, and I want this to be equal to pi 0. I should not put commas because it's a vector, sorry. It's a matrix representation rather. Right? So the way pi comma I is defined is 1 minus lambda if I is 0, 1 minus lambda minus mu if I is between 0 and n, and is 1 minus mu if I is equal to n. Right? So this defines the entire matrix. The rest of the entries are 0. So every row in P has at most 3 entries. So if I have to write my if I have to write the equations, so what will my equations be like? My pi 0 is going to be, what are the entries that are connected to? So 1 minus lambda times pi 0 plus mu times of pi 1, right? So what does this give you? Lambda times pi 0, rather lambda by mu times pi 0 is pi 1, right? Then what do I have for pi I in general? This is lambda times pi I minus 1, because you have a probability of lambda coming from I minus 1 plus 1 minus lambda minus mu of being at pi I plus mu times plus 1, right? So what will this be? So this I'll do, so times pi I is equal to I minus 1 right, and then pi of n is lambda times pi n minus 1 plus 1 minus mu times pi n, right? So now let's instantiate this. Let's instantiate this with pi 1, right? So what do I have? Lambda plus mu times pi 1 is nothing but lambda times pi 0 plus mu times pi 2. So what do I have here? So I have pi 2 is nothing but, what is mu 1? So it is lambda by mu times pi 0 times lambda plus mu plus lambda times pi 0. So is it, I'm messing up the signs? I'm sorry.
Above equation, just substitute value of pi 0. Pi 0 is u by lambda pi 1. So lambda lambda gets cancelled and pi 1 also gets cancelled. U pi 1 gets cancelled.
No, so which one do you want me to solve?
First Brown equation.
Okay, so this one.
Substitute pi 0 as.
All right. So okay, so like why not? Let's do that. So what do I get here? So let's say I have instead of substituting for pi 1, you want me to substitute for pi 0. Okay, so yeah, that's much simpler. Lambda plus mu times pi 1 is equal to, it's mu by lambda times pi 1 times lambda. Right, these gets cancelled off.
Mu pi 1 gets cancelled.
Plus mu pi 2. So this gets cancelled with this. Right? So what you have is lambda times pi 1 is nothing but mu times pi 2. Right? If you keep doing this, what you're going to get is pi I is nothing but lambda by mu to the I of pi 0. I mean, these have this, like, the similar what do you call structure. So now what we know also is that summation of pi I is equal to 1. Right? So what you get there is summation of, so like I'll take pi 0 common. So lambda by mu to the I, where I ranges from 0 to n, you get, so this is equal to 1. Right? So what is this? So this is a geometric sum, right? So even without this, we can actually say, like, pi 0 is nothing but 1 by summation of zero to n. So in particular, this gives us that pi I is nothing but lambda by mu to the I divided by summation I is equal to 0 to n. Let me just make a different index. Right? So you happy with this? So now, let's say here n is finite. If n is not finite, what will happen? Sorry? Right, so it becomes a like infinite geometric progression sum. So if n is not finite, in such situation you have pi I is nothing but lambda by mu to the I, and what is the GP?
1 by 1 minus lambda mu.
So that is nothing but 1 minus lambda by mu, right? So
If this ratio is less than 1, lambda by mu.
good. If lambda by mu is less than 1. Otherwise, it is like, it's a quantity that keeps on growing. Right? We don't have a convergent sequence. Good. Any questions? So this is a problem that was nothing related to Markov chains, but you actually analyzed the behavior of this queue at any given time as a probability distribution, right? So you have defined a probability matrix, and you've also defined the probabilities of people being in a particular. So you can assume that the queue starts with with no people, right? At any point of time, I mean, so at the beginning the queue is empty. You can assume that, and then you want to see like at time t how is this? What are the number of people in the queue? It gives you a way to analyze probabilistically some real world object. Make sense? So let's look at another problem, which is called so far you're clear with everything, right? Good. Right. So how many of you seen this problem before? Like, you have? So then help me out. Right. So what's the problem?
So there is a gambler who comes to play gamble with some initial set of money. So every time he bets, he wins or loses. He wins with the probability, he loses with the probability.
Right.
That's the
Right. So there are two players who have come to play. Right. So if it's fair, then the probability of winning is the same as probability of losing. Okay. So there are two players, player 1 and player 2. Right. So player 1, the situation is that, so at each stage, you either win or lose. So it's against each player, right? So 1 second. So the states, I have to define like a Markov chain based on this problem, right? What are the states?
So if you're coming with I money at your hand, then you go to I plus 1.
Right.
And then so you have a target, so if I win this much amount of money, then I'll stop the game. Or if I lose all the money that I have come with, or I hit 0, I stop the game. So it starts from I, it can go all the way till n.
So I'll define what the game is now. So for me, I am going to define my Markov chain as money held by a particular player, right? So the strategy, so the game is player 1 wins if, so he gains L1 money. So rather, so player 1 cannot lose more than L1 dollars, let's say. And similarly, player 2 cannot lose more than L2 dollars. Right? So if it is player 1, if the player 1 hits minus L1, he loses. If he hits plus L2, then player 1 loses. Player 2 loses. Right? So it says, so if player 1 loses, the money is going to player 2. So the game is set up in such a way that whatever money is lost by player 1, it goes to player 2. And whatever money is lost by player 2, player 1 gets it. Right? So that's a game. So initially assume that both of them are, so initially player 1 is starting with 0 money. Right? So here you are, so essentially like you can assume that you are going into credit of minus L1. Right? You owe somebody minus L1 and up till minus L1 is allowed. If you hit minus L1, you're out of the game. Right? So this is a simple game. So there is player 1. So starting with 0. With certain probability, he'll gain money, and with certain probability, he'll lose money. Right? And this is for this until minus L1, and this is until plus L2. If player 1 reaches minus L1, he loses. If player 1 reaches L2, he wins.
What about reaching minus L1? If after minus L1 that round again you lose, then you lose. Because it says player 1 cannot lose more than L1.
So let's say, sure, minus,
See one more state after L1, the losing state and the winning state, after which there's no more arrows.
I mean, let's say like, minus L1 is like once they reach minus L1, they lose.
Cannot lose L1 dollars.
Yeah, you cannot lose L1 dollars. So greater than equal to. Let's put.
But even if we create one, then we can have an arrow with probability 1.
Yeah, so even if you have a minus L minus 1, you can create a new state. You can have a transition probability, and then like at the probability 1, you stay there. That makes sense, right? Yep. So the question here is, so what is the probability that player 1 gains L2 before losing L1? So the probability in either direction is say half. Right?
So do we need the word before?
Yes.
I mean, if he wins or loses, then the game terminates. So, not sure.
Okay, so like to make it, so let's put this. So once you reach minus L1, you just like get stuck there.
So now we don't need the word before.
Yeah.
Also, last arrow we need to do.
Which house? Yeah.
Last one.
Sure. So then if I have the half, the before makes sense. So let's, for the sake of sanity, let's I can keep this. I don't have to make this finite then. Or like, yeah, let's keep this. So the reason I want to like look at this is I want to look at a different way of looking at things. So something which you have not seen so far. All it says is starting from 0, what's the probability that you want to reach 1? I mean, so L2. Yeah, sorry. Okay. There should be half probability.
Yeah.
Oh, this is no. So this is so this one L2, right? So there should be half and half.
Yeah.
So even this is half.
No, but we said ki if you just reach L2 or L1, you just said greater than equal to, right? So if you just reach it, then just stop. So if you've reached L2, then transition probability out of L2 is 0.
The transition probability of out of?
L2 is 0. If you said greater than equal to, reach L2, stop. And the transition probability out of L2 is 0. So L2 to L2 is again just 1, what you wrote before. It's just a question about greater than equal to or greater than.
So we can make a general case. Like
This what you wrote is greater than. What you wrote before is greater than.
No, actually, so no, wait. So what this says is like you can come back.
Yeah, so basically this is
So-
with half probably going to L2 plus 1.
Yeah. So hey, one second. So this is all fine. The previously it was still fine
Yeah, previously it's fine. It's still greater.
because the outgoing edges have to sum up to 1, not the incoming edges. So I'll give you a hint. So I can define something called. So this is a problem on Markov chains, and I'm going to define a quantity called Qj. Right. So what is Qj? Qj is probability of reaching L2 starting from $J. Right? So can you express this as conditional probabilities then? Right? So you have Qj. I can write this as,
either you can lose or you can win. So if you lose,
so basically it's either with probability half, I'm going to go to J minus 1.
then from
Right.
here win, that is Qj minus 1.
So what is this? This conditional probabilities, right? So probability of winning. So probability of winning from probability of going to L2. So with half probability, suppose my J is 0. With half probability, I am going to the state minus 1. With half probability, I am going to state 1. Right? So now this probability of winning from 0 is now can be, I mean, it can now be written as conditional probabilities, right? So probability, so either I go through this and or through this, right? At this step, the probability of winning from 0 is equal to probability of winning from -1 times half, because this is a conditional probability, and probability of winning from 1 times the conditional, this probability is half, right? So the other way to write this, Qj is nothing but half times Qj minus 1 plus half times Qj plus 1. With half probability you're going backwards, with half probability you're going forwards, right? And what is Q of minus L, minus L1? 0. And what is Q of L2? 1. And this is for all j between L2 and minus L1. Right? Does this make sense? And what we are interested in, Q0. So this is what we want.
Sir, why Q minus L1 is 0?
Because the probability of, so look at this. Once you go to minus L1, there's no way you can get out of it. Right? The probability of getting out is 0. Getting to, so once you reach this place, the probability of getting to L2 is 0, right?
The J is between L1 and L2.
Yeah, so the J is between, right? So this is, so now what is, if you solve this, what you will get is, so the answer what you'll get is, so Qj is nothing but L1 plus J by L1 plus L2. And what we are interested in is Q0. Right? So again, it's a very generic problem. You're modeling it as a Markov chain. So here conditional probabilities are what we are using to state this equation. These equations that we built up, these are conditional probabilities. Right? Or like, so this could also be thought of as the number of steps needed. So I said there's a probability. If you ask me about the number of steps needed to reach L2, even that could be phrased as follows, right? So what would that be then? If you ask me number of steps, so let's say the number of steps from, so steps from J, starting from J, to reach L2 is half times S of J minus 1 plus, because you're going in one step, you're going to Sj minus 1 plus half times Sj plus 1 plus 1, right? So this kind of equations you can form whenever you have conditional probabilities like this. You can come up with equations like this. So how do you come up with the equations? Just look at conditional probabilities. So with half probability, you're going to Sj minus 1. So here Sj denotes number of steps needed to go
From J to L2.
to go to
L2.
L2 from J, where J is between, strictly between minus L1 and L2. Right? Good. So there are multiple ways to look at this probability. Is all I'm trying to tell you. There is more information hidden in this transition matrix. Is what we're trying to recover, right? So let's stop here.